poles. Where are you? There you are. Okay, so it's worth stating that for this question, we actually could solve this question using the techniques that we learned way back when we were doing differentiation and we were doing optimization there. You can do it that way. I would suggest you try doing it using Lagrange multipliers though, right? Because it's very easy for us to give you a question that needs you to use Lagrange multipliers. And that's sort of like what we want to practice here, right? Because I promise you 100% that there will be a Lagrange multipliers question on the final exam, right? So you just want to make sure that you get a little bit of an opportunity to practice that, and especially solving them, because it's very ad hoc, right? You kind of like have to look at your nonlinear system of equations and figure out the attack and procedure that you want to take, depending on what actually comes out, right? There isn't like an algorithm for solving it, not like linear systems, right? Right, that's a great question. Yeah, what is the purpose of Lagrange multipliers? Maybe I can draw something here while we're at it, but basically, here, let me draw something. Let's get annotations going. So you remember when we were doing single variable calculus and we had to check the endpoints, right? So you could have a function and maybe that function looks something like this. And you could find the critical points, right? But you still had to check the endpoints. And the reason is that the derivative, like those aren't critical points, right? Your derivative can't necessarily detect those. So you have to be able to check your boundary points and see maybe they're actually the global min and global max. And the picture that I've just drawn, they are, right? The left endpoint is the global min, the right endpoint is the global max. And if we just computed critical points, we wouldn't have been able to see that, right? Because the derivative is not equal to 0 at either of the two endpoints. So the same sort of thing is true in multiple dimensions, right? When we do multivariate calculus. Now, obviously, this one's a little bit harder to draw, so I'm not 100% certain I'm going to be able to. But this process of finding the critical points of the gradient and then using the Hessian and looking at that second derivative test, that's great. That works on the inside of a space. So let's say, this is the space you're working on. And I'm going to try and draw what its graph might look like, but maybe the graph looks something like this. Right? And then it sort of like circles around. Do you know what I'm saying? It's sort of like an eggshell that you sort of, you've taken half of an egg, but it's sort of wavy along the outside. So your critical points will be able to detect the maxes and mins that occur on the inside of this thing, right? That occur like on the inside of here. But it's not going to be able to detect the endpoints along these outside portions, right? Because a maximum could occur at these endpoints, but not be critical points, just like what happened on the left-hand side. So what Lagrange multipliers does is it's specifically how we figure out what the maximum is when we can't use critical points, right? So often we use this when we're doing like looking at the boundary of some sort of shape, or if we've got like, this example works well, right? So this example, we're trying to optimize this two-dimensional function on this one-dimensional sort of shape, right? It's basically just a curve. And again, critical points aren't going to do us any good for that because you just need sort of like more space to move around when you're doing multivariate stuff, but don't worry too much about this or that. The idea is that we need Lagrange multipliers to tell us what the maxima and minima are on the boundary, because critical points won't be able to detect that. And yeah, in one dimension, that's easy. Yeah, exactly. It's very similar to one variable functions, but in one variable functions, the boundary of your interval is just 2 points, right? It was like A and B. It was the left endpoint and the right endpoint. Now, when we look at the boundary of a set, it's, it has infinitely many points, right? It's this entire, like in this case, it's sort of the outside of this square. So we can't just plug in every single one of those points into the function, right? There's just too many of them. So what Lagrange multipliers allows us to do is figure out what the maxima and minima are on that boundary without having to appeal to critical points. And there is secretly like some sort of critical point thing going on here, but it's hidden in how you actually derive the formula for Lagrange multipliers, which obviously we're not worried about because it's a little bit complicated. But that's what we use it for, okay, to find the boundary, or this is Lagrange multipliers is checking the endpoints for a multivariate optimization. Yeah, generally you're trying to find global maximum. Here it says, just find the minimum. This function doesn't have a max and it doesn't have any global or like local mins even. So basically what you find is going to be a min. And you can convince yourself that what you get isn't going to be, can't be a max, because if you look at the function you're trying to optimize, you can just make x as big as you want, right? You can also make y as big as you want, but basically x and y can be as big as you want them to be. So this function definitely doesn't have a maximum, but it could have a minimum, right? Right, exactly, because it effectively is a constrained optimization problem. That is what Lagrange multipliers really is. It is a method of solving constrained optimization. In fact, if you check the notes, I'm pretty sure this section is called constrained optimization. And because it is a two-variable optimization problem, like I said, you actually can solve this using the techniques that we learned however many weeks ago. It was 5 or 6 weeks ago when we first learned about derivatives. And you can try that, okay? So I suggest after you do this by Lagrange multipliers, try solving it the old-fashioned way and see that you get the same answer. The difference, though, is Lagrange multipliers works no matter how many variables you're given, okay? And the only way that our old-school constrained optimization problems are solvable under those techniques that we learned so long ago is if it's exactly two variables, right? So only x and y. So after this question, we're going to do an x, y, z example, right? Where we actually have 3 variables. And then that one we can't solve that way. Mm-hmm. Note as well for the multiple choice portion, now obviously your test won't be multiple choice, but for the multiple choice, you can actually test whether your answers are correct, right? Like you can just plug these points into your function and see which of them is the biggest and which of them is the smallest. Obviously, that's not what I want you to do, but you could do it that way if you wanted to. Okay, so I'm going to lock this up in about a minute. That'll be the 10-minute mark. Okay, 10 seconds. All right, okay, let's take a look at this. And so the classes split looks like between A and C. So immediately, if we just had to determine whether A or C was better, let's just try plugging A into our function, right? So if we plug plus or minus 1, 0 into my function f here, right? So if I took this thing and I plug that into f, what would I get? So I get f plus or minus 1, 0. That's going to be 1 squared plus 0 minus 2 squared. So that is what, 5? And then if I do it for this example, root 2, 1, I would get root 2 squared plus 1 minus 2 squared. So that's 2 plus 1. So that's 3, right? Okay, so between those two, C has to, like, assuming they both satisfy that equation, x squared minus y squared equals 1, and they do, that immediately tells us the answer can't be A, right? Because C is a better point. So C definitely is the correct answer. In fact, I think of the options in B, the left side does live on the curve, but I don't think the right side even does. So that kind of eliminates B for that reason. Now, again, obviously that sort of technique doesn't work in a test because it's not multiple choice. But again, sort of as a sanity check, you can totally do that thing and check if your answer is correct. So let's go through this. This is a little bit long. If something doesn't make sense, you need to scream at me, okay? Because again, I promise you there's a Lagrange multipliers question. So you need to know how to do this stuff. Okay, so we've got this function. We've got f of x, y. So all I'm going to do, I'm just going to repeat the question so I have it in front of me here. Y minus 2 squared, like that. And it's subject to the constraint that x squared minus y squared equals 1. Okay, now according to Lagrange multipliers, what I want to be able to do is that when I have this constraint function, I want to be able to write that as the 0 set of something. We call that the 0 locus, or the 0 level set. So the way that I'm going to do that, I'm going to take this function and I'm basically going to move everything to one side. And that's the thing I'm going to call g. Okay, so I'm going to get x squared minus y squared minus 1, like that. Yeah, it's called, yeah, sure. So here's what I mean. So that so x squared minus y squared equals 1 is the same thing as saying g of xy equals x squared minus y squared minus 1 is equal to 0. Okay, so this is called a 0 locus sometimes, or a 0 level set. Okay, those are sorts of the words that we use for it. But you see that those are the same thing? Because if this is 0, then we just put the 1 on the other side, right? And we get that. So that's how sort of Lagrange multipliers is stated. It says, g of xy is equal to 0. And in order to figure out what that is, you take your constraint and just shove everything onto one side, define that thing to be your function. Okay, now for Lagrange multipliers, what do we know? So the whole thing about Lagrange multipliers is it tells you that there's some lambda such that this is true. Okay, and this thing is going to give you a system of equations, generally a nonlinear system. Okay, but whatever the solutions to that thing are, those are your candidates for being maxes or mins. So it comes at a price, right? Because otherwise we have no idea how to even begin looking for maxes and mins. But if we solve this nonlinear system of equations, at least we have a chance. So here are my functions, right? I've got f up here. I've got g here, so we can compute their gradients. All right, so I'm going to get the gradient of f is 2x times 2 times y minus 2. Okay, and the gradient of g, I'm going to write it down, and then again, somebody can yell at me if that doesn't make sense. 2x negative 2y, like that. Okay, everyone good? Yell at me if something there doesn't make sense. All right. So again, Lagrange multiplier says these two things are equal up to this thing called lambda, which is the Lagrange multiplier. That's when we say Lagrange multiplier, we're talking about lambda. In fact, that's why it has the letter lambda. Lambda is like the Greek L, right? So let's set these two things to be equal to each other. So if setting the gradient of f to be equal to lambda times the gradient of g, we get this. We get 2x is 2x lambda, and 2 times y minus 2 is negative 2y lambda. How did I get the 2y? So remember, g of x here, it's x squared minus minus y squared minus 1, right? So the y derivative of g is, well, what's the derivative of negative y squared with respect to y? It's negative 2y, right? Does that make sense? Because remember, the gradient is just the vector of partial derivatives, right? So x derivative and the y derivative. Okay, is everyone good with these equations? Right, this left-hand side, right, that's the gradient of f, and then the right-hand side is lambda times the gradient of g, and we've set these to be equal to each other. Okay, everyone's good? Okay, so I don't like these 2's. I think that they're just kind of annoying. So we can get rid of them because every single, there's a 2 in everything. So let's sort of just make this a little bit easier. So we get x is equal to x lambda, and then we're going to get y minus 2 is equal to negative y lambda. And again, my sort of thing is like, I see that there are x's in that first equation. I see there's x's on both sides. In that second equation, I see there's y's on both sides. I kind of want them to be together, right? Because that's just, it's going to make my life a little bit easier. So why don't we sort of put these things together? 1 minus lambda x is 0. And then what is this one? So y plus y lambda. So y times 1 plus lambda is equal to 2. Okay, so all I did there was just a little bit of manipulation. I just put all the x's on one side, put all the y's on one side, sort of like put the constants on the other. You don't have to do that. It's just, for me, this is, a nice organizational trick, because now I can look at this and I can say, okay, is there any, based off of the equations that I see now, is there anything I can infer? Is there, obvious cases? And if I look at, here, maybe let me number these. If I look at equation 1, I'm like, yes, okay, I can do something with equation 1, right? Because I've got this product of things being equal to 0. Boom, I'm in a place now where I can apply cases, right? Because if that product, 1 minus lambda times x, is equal to 0, one of those two things has to be 0. So I get case 1, 1 minus lambda is 0. Case 2, x is equal to 0. Great, I can make some progress. Okay, so is that good? Yeah, exactly. Those are my two cases. X is 0, lambda is equal to 1. Right? So I got a direct message asking if those are the cases. Exactly. And we can't do that with equation 2, right? Like with equation 2, I don't know anything. Y could be anything. 1 plus lambda could be anything. The product of two numbers being equal to 2 doesn't tell me anything about those two numbers. 0 is a really special number in that case. So I'm kind of trying to make 0 show up. Okay, so we've got two cases. Now let's do the x equals 0 case first. Okay, so from equation 1, either x equals 0 or lambda equals 1. So let's do x equals 0 case. Okay, so now, I guess, actually, you know what? Let me, so would we need to evaluate cases for equation 2, or is it pointless? Yeah, that's a good question. Generally, it's going to be useless in this case. I would say we're not going to be able to glean any information from equation 2 directly. Now, once I've got my cases, one of the things I'm going to do is start to throw those numbers into equation 2 to see what sort of information I can get out of it. But you're right, at this point, I don't think I'm going to get anything useful out of equation 2. So it's not going to govern, how we proceed at all for that reason, right? Because I don't, I can't say anything. Sure, okay. Same, just remind me. Now at this point, I do actually kind of want to add the third equation back in just so that we have it. So x squared minus y squared equals 1. Okay, I just kind of want to put this back in. Right, okay. So just as a reminder where that equation came from, it actually is the original constraint, right? So whenever you're solving these Lagrange multiplier questions, don't forget your original constraint is one of the equations that you can use. So sometimes, like most of us as mathematicians, we sort of just remember it in the back of our heads, so we usually don't write it down. But I think that when you're first learning Lagrange multipliers, you might want to actually explicitly include it in your list of equations so you don't forget that it's there, right? Because if you look at this system, you'll notice that we have three variables, right? We've got an x, we've got a y, and we've got a lambda. We've got no idea what the lambda is. If we want any chance of solving for those three variables, we need three equations, right? And the gradient of f being equal to the gradient of g will only give us two, and that will always be true, okay? If you've got n variables, the gradient of f being equal to the gradient of g will only give you n equations. And you need that n plus first equation in order to be able to solve it. So I think you should just include that constraint equation explicitly at this point so that you know how to move on. Yeah, generally for n unknowns, you need n equations, right? And the Lagrange multiplier question will always have n plus 1 unknowns. So we need that n plus first equation, and that's the constraint. Okay, so we've got that. Now, okay, if x is equal to 0, well, equation 2 still doesn't tell me anything, right? Because equation 2 doesn't have any x's. So I'm going to go straight to equation 3. And exactly, Brandon. Yep, that's right. So in equation 3, this now becomes, so we get 1 is equal to x squared minus y squared. If I plug x equals 0 into that, I get 1 is equal to negative y squared. And this is impossible, right? Like we can't do this. And so we say this case is impossible, right? Which has no solutions. So we kind of just throw this case away immediately. It's not useful. All right. So that's that case. That was nice and easy. So the next case is where lambda is equal to 1. Now, it's really, really rare that you actually solve for lambda and use that to help you out, but it does happen on occasion. And this is an example. So we've got lambda is equal to 1 here. And now, again, I'm going to look at my three equations here on the top right-hand corner of your screen. And I'm going to say, well, only one of these equations has a lambda in it, right? So that's probably going to be the equation that I use next. So if I plug this into equation 2, I get y times 1 plus 1 is equal to 2. That's the same thing as 2y is equal to 2, or y is equal to 1. Yes, yeah. Yeah, 1 equals x squared minus y squared here. Maybe let me make my y's more obvious. Yeah. Okay, so cool. If I plug lambda equals 1 into equation 2, boom, I have y, right? I've solved for y, I figured out exactly what it is. And now that I've solved for y, okay, equation 1 is useless to me because it's 0 is equal to 0. Equation 2 I've just used. So now I can use equation 3 in order to figure out what x is. So for the cases, we need to use an equation other than the one we derived the cases from. Yes, yeah. This is a very good point. So the question is, when we like are starting to go through our cases, yeah, we can't use equation 1 here because our cases are designed so that equation 1 is satisfied, right? Like think about it. If I plug x equals 0 into this equation, into equation 1, what do I get? I get 0 equals 0. That equation is now useless to me, right? Same sort of thing. If I plug lambda equals 1 into equation 1, I get 0 equals 0. So that equation is useless. So that's the sort of idea. It's true. You generally, I mean, you could try and use that equation if you really wanted to, but it's going to be useless to you because you chose your cases such that that equation is useless, right? Like you've ensured that that equation is true. That's where your cases came from. So yeah, you generally kind of skip it. Like I said, you could try and use it if you wanted to, but the reality is you just can't get anything from it. Okay, so we've found now, we've got y is equal to 1. So now I'm going to plug this into equation 3. So I get 1 is equal to x squared minus y squared. But we know what y squared is. So that's going to be x squared minus 1. And I can solve this equation for x squared. And then I can solve that for x. Right? And there we have it. I'm done. I've now exhausted all of my cases, and I found two solutions. Thus, there are two solutions, plus or minus root 2 and 1, like that. Okay. Now, unfortunately, there is no second derivative test. You don't know whether anything that you found is a maximum or a minimum. So when you're trying to find global maxes and mins, your answer here is to just plug everything back into your function and figure out which of those numbers is the biggest and which of them is the smallest. In this case, you need to exercise a little bit of, you have to think a little bit about the equation. Remember, so it's x squared plus y minus 2 squared. Look at this and say, yeah, okay, that function doesn't have a maximum, right? Like even on this curve, I can make x's and y, the x term and the y term, as big as I want them to be. So I can make f really, really big, as big as I want it to be. So no maximum actually exists. So the Hessian doesn't work because the Hessian, like the second derivative test, only works if we have critical points. And these are not critical points, right? Like that's what Lagrange multipliers does, is it helps us find maxima and minima when we can't find critical points. So the Hessian matrix test only works for critical points, right? And it's sort of the sad reality is that we don't have anything that can help us out here. But the reality is that, this is better than nothing. So you kind of have to then at this point, in real life, what you do is you'd go and you try and make some sort of argument about this function, or plug it into Desmos and say, look, this function has a minimum, but it doesn't have any maxes. So the things that we found are clearly mins. You have to, that's going to depend on your function, and you generally can't tell. But it would be the same sort of thing. Like if I gave you this function, let's say we were doing single variable calculus, and I said, find the max on 0, infinity, right? The answer is that there is no max because you know what this function looks like, right? But like, how would you answer that question for me in single variable calculus? You say, well, look, I can make this function get as big as I want it to be, right? Like I'm allowed to choose any x greater than 0. So, by choosing bigger and bigger x, the function f gets really, really big as well, right? That's the sort of argument that I think the people in this class would make. If we were doing more complicated mathematics, there is a way to actually formally prove that, but that's not the sort of thing we would do here. So you'd look at this function, you'd be like, hey, look, I can make this thing as big as I want. Therefore, this function doesn't have a max. Do you know what I mean? So that's the sort of thing that you would do there. And that's unfortunately the sort of thing that you're going to have to do here. You're going to look at this function and say, look, it keeps getting bigger, right? Like there is no upper bound to the size of things that we can put in here. Okay. So that actually took a fair amount of time, right? That took us 30 minutes between me giving you 10 minutes to solve it, and then it taking me like 15 minutes or so to write it up. Now, you guys want another one? Or because we're going to have to go into office hours if we do this. Do you guys want to try another one, or like how do you feel? Should we just kind of call it and then we can go into office hours? What do you guys want to do? Another one? Okay, sure. So Simon, let me answer that in a second. Maybe let me get the next one going up here. All right, so let's try that. Yes, tutorials will be next week like normal, and they will cover this sort of stuff. So it'll also be another opportunity for you to do more Lagrange multiplier stuff, okay? So yeah, so I got a direct message saying like, I understand the math, but what are we trying to solve for here, right? And in that last question, so let me just write on this, and I'll get the polls going up again. In that last question, what Lagrange multipliers did was end up giving us 3 equations and 3 unknowns, right? And what were those equations? It was x times 1 minus lambda is equal to 0. It was, what was the other one? Y times 1 plus lambda is equal to 2. And x squared minus y squared equals 1. So what we're trying to do is we're trying to find the values of x, y, and lambda, which satisfy this system of equations, this nonlinear system of equations. And what Lagrange multipliers does is it says if a max or a min does occur on that boundary, it is a solution to this system. And just like when we were talking about critical points, not every solution to this system will be a max or a min, but if a max or min does occur, it is a solution to this system. So what we're trying to do is we use Lagrange multipliers, we figure out what this system is, and then we try and find all the solutions to that linear system, because those will be our candidates for being maxima and minima on that boundary. So does that make sense? Well, except we're not finding critical points, right? So we're not actually finding critical points. Lagrange multipliers gives us this system of equations. And then all we're trying to do is find these solutions. If we can find the solutions to this system of equations, then we're done. And we know that if a max and min occur, it must be amongst those solutions. And then we can just plug those numbers into our function and see which is the biggest and which is the smallest. Right, so you remember like when we were doing linear algebra? And right, when we were doing linear algebra, you might be given a, a system of equations like, and what were we doing in that case? Like like, do you remember when we were doing linear algebra? And we'd give you something like this, and we'd say, find the x, y's, and z's which satisfy the system, right? Exactly. You're trying to determine exactly what numbers you could do and plug them in, and it would satisfy every single one of these solutions simultaneously, right? So in our previous example, what did we find? So we found that x was plus or minus √2. We found that y is equal to 1. And we found that lambda is equal to 1. And what you see is that if you plug those three things into the system of equations that I've put into a box here, every single one of these equations is true, right? And so all three of those equations are true simultaneously. So it's very similar to what we were doing when we were doing linear algebra. But when we were doing linear algebra, we were guaranteed that you would never have anything like x squared or y squared or e to the x, or right? It was nothing like that. It was always just constants times x plus a constant times y plus a constant times z. That's why it's called linear algebra, because everything is either x, y, or z, not x squared, not y cubed, not 1 over z, nothing like that. But the tricky thing that we get with Lagrange multipliers is that it doesn't need to be linear, right? So we can't use the tools that we learned from linear algebra in order to solve these systems. And that becomes much harder to do, right? You kind of have to wing it and say like, all right, I'm going to look at these things and see if I can guess all the cases, but it's not super obvious. So these are the sorts of things you have to practice, because there isn't an algorithm, right? We had an algorithm for solving linear systems. We could use Gaussian elimination, right? These are much harder. Exactly, yeah, those solutions are the possible max-min candidates. Just like when we were finding critical points, remember, not every critical point was a max or a min, but if a max or min occurred on the inside of on the interior of a set, not the endpoints, then if a max min occurred, it had to be a critical point, right? We proved that, we talked about that theorem. So it's the same thing here. Once we find the solutions, not every single one of those will be a max or a min, but if a max or a min occurs, it has to be one of those solutions. Yeah, exactly. Saddle point is an example of that sort of thing. Like when you're doing critical points, you can have critical points that aren't maxes or mins, and a saddle is a great example. And then again, this is not critical points, right? This is different because now we're working on a boundary, but we're still looking for the solutions, because we know that a max or min, if it occurs, is a solution to this system. No, it's okay. This is hard. Lagrange multipliers is tough. And I would love to give you some sort of physical intuition about like why Lagrange multipliers is true. But the reality is that that's also really tough. It's a really slick sort of geometric argument, but it's not at all obvious. And the amount of math it would take for me, like I'd have to introduce a lot of math in order to be able to explain why this is the right equation. And again, there are critical points occurring, but they don't show up, like you don't see them. But there are secretly critical points hanging around here. It's just they've sort of been hidden, and we just give you, the equation that matters. This gradient of f is equal to lambda times the gradient of g. That's the important equation. That itself happens to be a critical point for some other weirder function, right? Is sort of what's happening.
I don't know about that either, to be honest with you. So like, if you guys are kind of confused about this, it's not like, don't think it's something that you should have known about, because like I don't think of myself as like someone that's excellent in math, but it's definitely well above my knowledge.
Yeah, it's tough, right? Like it's not at all obvious. It's the sort of thing that like we might prove in advanced second year. So in an advanced multivariate calculus class, if we were doing it, we might prove it in that class. And even then those students really, really struggle with it, right? So it's not an obvious thing at all. So basically those solutions are min and max candidates within the set, but there's no guarantee that they're max or min. Right, yeah, exactly, Simon, yeah. Can I give an example of how we'd visualize these points graphically? Like those critical points that are not, yeah, okay, so I think we gotta go back to like the egg picture, right? So suppose that, you know, when I graph the function, you know, it looks sort of like this. Okay, so do you see what do you see sort of what I'm drawing, like in terms of the function, right? And this sort of ideas is this thing sort of like looks like this, right? And so what Lagrange multipliers will do is it'll point out these points, which sort of look like they're critical points, right? They sort of look like they're critical points, but they're sort of only critical points on the boundary. Yeah, this is supposed to be a 3D shape. Like, again, think of it as like you took an egg and you sort of like cut the top off the egg, but it wasn't a perfectly straight line. Like there were sort of ridges and grooves around it, right? So what Lagrange multipliers is doing is it's figuring out where basically if you sort of drew a line around your boundary and sort of just made a cut and then, you know, flattened it. So you drew it in a plane. If you did that, what would the critical points of that thing be? That's what I'm saying. There actually are critical points hanging around here, but they're a little bit hard to see. And so it's, you know, this process of Lagrange multipliers is finding these, you know, local maxes, these local mins, these, you know, critical points that are neither local maxes or local mins. And then you're just going to test them all. But again, there's no, right? Like you can't use a multivariate critical point to detect these things because they don't need to be multivariate critical points, right? Like think about this, if this is a bowl, right? Like the paraboloid, and it just keeps on going up forever. But then I cut it and sort of, you know, draw a line around it. You're not going to see a multivariate critical point there because the function is actually just shooting off to infinity, right? It's only when you just sort of look at the boundary itself that you're actually able to see that there are these sort of local maxes or mins in this one-dimensional projection of the boundary. Yeah, exactly, Simon. Yeah, only around the border. But how come those are not considered local mins or max, like geometrically speaking? Right, okay, so how do I do this? I think I need like a marker or something. Yeah, maybe let me try and do this. No, it's okay. This is tough. And a big part of this is that like you're trying to visualize this in three, you know, trying to visualize in multiple dimensions is hard. All right, and let's see if I can make these join up. The use of primitive visual aids, as we say in the biz. Okay, let's see. Okay, so if I had a little bit more talent, I would maybe cut this out, okay? But you see the line on this thing, right? So let's say this is my shape, okay? This sort of like represents the graph. Actually, maybe let me sort of like fill in underneath it. Now I gotta take it apart. Okay. Okay, so the function itself is sort of like the filled in area, right? And you can see there's this like three-dimensional shape that I have, okay? Now a multivariate critical point is where if I were to like draw a tangent plane, the tangent plane would be like parallel to my desk, right? So let's say maybe even this thing like tucks in at the bottom here. Obviously, this is very hard to do with a piece of paper, but imagine that it sort of cups in at the bottom. Then a multivariate critical point is going to be where if you draw the tangent plane, it's just flat. Okay, so this is not a multivariate critical point. You know, this is not a multivariate critical point. You're going to get that multivariate critical point only when you're actually lying flat, okay? So when that three-dimensional or that tangent plane is parallel to my desk. Does that make sense about what a multivariate critical point is? Right? So just like a critical point is a horizontal tangent line, a multivariate critical point is a horizontal tangent plane. Okay. So far, so good? Okay. Now, if we look at this line here, so again, sort of pretend that I took a pair of scissors and sort of like cut the top out of there, okay? So if I were to compute the gradient at that point, you can see it's not a critical point, right? Like it's the tangent plane is actually really, really steep. But nonetheless, when I only look at the boundary, there is actually, this is a local max of the boundary, right? Even though the tangent plane at that point is like really steep, right? Is really steep. On the boundary, it is actually a local maximum. Do you all see that? Does that sort of make sense? And so the critical points can't detect that this is a local max because the tangent plane here is not flat, right? It's not horizontal. But nonetheless, there is a maximum along this boundary. No, because yeah, you can't, like, even if I'd cut this off, you can't put a plane there because the tangent plane sees the whole shape, right? The tangent plane sees the whole shape. So you can't just park right at the top of the wave. You can't just park something like that. That doesn't make sense because it knows, okay, the gradient knows that the shape actually does continue to go up, right? Just like in one dimension, if I drew this graph and I tried to compute the derivative here, well, that derivative knows that the function actually keeps going upwards, right? You can't just put a horizontal tangent here and say, oh yeah, it's a critical point. No, because the gradient, the derivative knows that the function actually keeps going. Does that make sense? Right, so we can't just say like artificially here, we could put this sort of like horizontal tangent plane. That doesn't work because the gradient knows that this function actually continues to go upwards.
It's kind of like magic.
Yeah, right, just derivatives know that that stuff is there. So does that make sense? Does everyone sort of like see why these aren't actually critical points? These are not multivariate critical points, but like it's only when I sort of trace around the boundary and think about those as being like one-dimensional things. And it's only, and this is actually more or less how the proof goes, right? The proof of Lagrange multipliers is basically take this thing, flatten it out, so it becomes the graph of a function in just R, like, the graph of a normal function, and then find the critical points of that thing, and then glue it back together, right? And that's more or less how the proof actually works. But that's not good enough to find that. It's still not multivariate critical points, right? That's not good enough. It won't give you those two. So is everyone okay with that? You kind of see. Okay, so let's see where we are because we're like 15 minutes into the, wow, that time actually really flew by. So we're 15 minutes in, and if I end this and then say share, that's pretty good actually. So 64% of you said D. D is the correct answer. Again, maybe that's one of those things where you could just sort of plug it in and see how it works out. But let's see, how would you actually get this, right? Like if it wasn't multiple choice, how would you actually solve for this? So let's turn off annotate. All right, see Aziz. Okay. Is the Lagrange multiplying the maxes mins just on the boundary, which cannot be critical points to this? Yes, exactly, Simon. That's a great summary. Lagrange multipliers is finding maxes and mins, which are just in the boundary and which cannot be critical points due to the 3D shape extending further up outside of the boundary. That is a phenomenal summary of what Lagrange multipliers is doing. So yeah, exactly. I think you have it. Sure, Curdy. Yeah, here, let's cover this and then I can answer some of your questions. I know a lot of you are kind of like thinking about assignment 12 here. So we've got, this doesn't take too long, I think. Well, it probably takes about as long as the last one. So x plus 2y plus 4z. Okay, and we've got x squared plus y squared plus z squared is equal to 7. Okay, so again, we have to figure out what the constraint function is. And the way that we do that is we take, x squared plus y squared plus 7, we put everything on one side, right? So we're going to get this function, gx, y, z, is x squared plus y squared plus z squared minus 7, like that. Okay. Now we have to use Lagrange multipliers. So we're going to compute the gradient of f, we're going to compute the gradient of g, and we're going to set them to be equal to each other. Now, as a little tip, and I think I even mentioned this in the video, strictly speaking, we really shouldn't do this. But when I compute my gradient, I actually kind of like to draw them vertically, like this. Okay, so the gradient here is just going to be 1, 2, 4. Normally, we'd write that as like a row vector. I like to write them as a column vector, and you'll see why in a second. So if we do this, we're going to get 2x, 2y, 2z. And the reason I like to write them as a column vector instead is because I know that the gradient of f is lambda times the gradient of g. It sort of lets me just read off the equations, right? So setting the gradient of f equal to lambda times the gradient of g. I'm just going to read across the rows, right? And I'm going to get 1 is 2x lambda, 2 is 2y lambda, 4 is 2z lambda, like so. Okay. And if you want, you can do a little bit of simplification here. So we get 1 is equal to 2x lambda, 1 is y lambda, and what, 2 is z lambda. That's just me sort of doing some cancellations there. You don't have to do it. That's okay. Again, sort of better that you make those mistakes now than on a test, right? Like this is exactly the right time to make those mistakes and be like, oh, okay, maybe that was silly. How do I make sure I don't make that mistake going ahead, right? So yeah, totally. This is the time to make those mistakes. Okay. Sorry, let me make sure clear this is a 2 and not a z. So now the problem is that I look at this. Oh, you know what? Sorry, let me also include my constraint. We need to, right? I was saying we were going to do that. So is equal to 7. So let's include that. So unlike last time, I don't see, an x on the left side and an x on the right side so that I can, combine them and get 0 or something like that. I'm not seeing that. But what I am seeing, like when I look at this equation, what I say is, okay, what if I solve each of these things just for x? You know what I mean? Sure, I can. Yeah, just give me a sec. So what if I just solve each of these equations for x? So first of all, lambda can't be 0, right? So note, lambda is not equal to 0. Do you see why it's not equal to 0? Why can't it be 0? Exactly. If lambda is 0, then this equation here is 1 is equal to 0. This is 1 is equal to 0. This is 2 equals 0. That's nonsense, right? That's not possible. Exactly. So, right, lambda can't be 0. So in particular, I can divide by lambda. So what is this going to give us? So I'm going to take these first 3 equations. Ooh, yeah, you could totally do that. So a suggestion came in, which is like, could we set 2x to be equal to y? Absolutely, you could. You could set 2x is equal to y because those two things are equal. Or if you wanted, you could do 4x equals y equals z, 2y, sorry. 2y equals z. Yeah, that's a great way of doing it, Arsan. So why don't we actually do that? So does everyone see this equation? If this is true? Let me just double check this. Wait a second, it's 2. Let me just make sure this is right. So 2y, yeah, I think this is fine. Right, does that make sense? Everyone agrees? Okay. So now what you can do, okay, sure, yeah, let me explain this one a little bit more. So let's take these 3 equations now and write them. So I get something like 2x is equal to 1 over lambda, y is equal to 1 over lambda, and z is equal to 2 over lambda, right? Do you agree? I can divide by lambda because lambda is not 0, right? So, okay. And actually, maybe let me just keep this as z over 2. I just want the right-hand side to be all 1 over lambda. And because they're all equal to 1 over lambda now, they're all just equal to each other. So 2x equals y equals z over 2. Does that make sense? And that is this equation, right? It's just instead of having z over 2 as a fraction, I multiplied everything by 2, and that gave me the same thing. So yeah, Arslan, great idea, 100%. Let's do it this way instead. So once you get this, 4x equals 2y equals z, now let's plug that into this equation. All right, so we're going to get x squared plus, now we know that y is equal to 2x. So normally we'd put y squared here, but now we're going to put 2x squared like that. And then we know that z is equal to 4x like that, and that's equal to 7. Okay, so is everyone all right with that? Does that make sense? Like Agam, yeah, that is what I would do, but I think when I did it, I didn't get root 3 over 2. I think I got 2 root 3. So are you saying that when you got this, it did, actually, is that what I got? Let me double check. You solve for lambda. So we know 2x is 1 over lambda, so you get 2. Oh, no, yeah, I think that's okay. Yeah, I think that is okay, Agam. I do think that works out. And that's actually how I did it originally, but I like this suggestion a lot, so I kind of want to pursue this. This is, okay, maybe this is z over 2, right? And that's because 1 over lambda, sorry, this is z over 2. My z's and my 2's look kind of similar. Davin, does that make sense? Maybe, maybe not. Okay, well, Davin, you let me know if that doesn't make sense. Okay, cool. So once we do that, we get this. And the reason why we might want something like that is now there's only one variable, right? This equation only has a single variable in it. So we're probably going to be able to solve it. So let's expand this out. We're going to get x squared plus 4x squared plus 16x squared equals 7. If we add all that up, we're going to get 21x squared is equal to 7. And so that means that x squared is equal to what? 7 over 21, so that's 1/3. So that implies that x is equal to plus or minus 1 over the square root of 3. Okay. And then, again, we know that up here, y is equal to 2x, right? So that we can just use that immediately. 2 or plus or minus 2 over root 3. And then we also knew that z was equal to 4x. And that is plus or minus 4 over root 3, right? And that is, yeah, okay. So this gives us now potentially a whole ton of solutions, right? This actually gives us 8 solutions. So this gives 8 solutions. So plus or minus 1 over root 3, plus or minus 2 over root 3, plus or minus 4 over root 3, right? So there's 8 solutions here, but what does the question ask for? It asks for the maximum. So what you would do is you'd go back and you'd plug all those functions back into this thing, right? This was our original function, x plus 2y plus 4z. But hopefully, instead of actually plugging them in, hopefully what you see is the maximum will occur when all of x, y, and z are the same sign, right? When they're all positive. Do you know what I mean? Because if like x and y are positive, but z is negative, there's going to be some sort of cancellation there, right? So you want all to get the maximum, to make this function as big as it can be, you want all of them to be positive. And so that's how we get the right answer without having to plug them all in, right? Okay, Christian, give me a second to do that. And then so the minimum by the same logic will be when they're all negative, right? So the minimum would be negative 1 over root 3, negative 2 over root 3, negative 4 over root 3. So if you really want, you can plug them all in, pull out your calculator, figure out which is the biggest and which is the smallest, but there's sort of like, a nicer way of doing it. Say, obviously the maximum occurs when they're all positive, the min occurs when they're all negative. Okay. Now it's asked the max and min thing. Sure. Okay. So just think about it. Like if I gave you the numbers 1 plus or minus 1, plus or minus 2, plus or minus 4. Let's not even worry about the root 3, right? Because they all have the root 3 in them. And I said, add, plug these numbers into this. When do you, what choice of signs gives you the biggest number? Well, the choice of signs which gives you the biggest number is when they're all positive, right? Because if I, so 1 plus 2 times 2 plus 4 times 4 is going to be bigger than if I put a minus sign in front of one of them, right? Because if I put a minus sign in front of one of them, then it's going to actually, take away from my maximum. So I really want to just make sure that they're all positive in order to get, sort of the best thing out there. Okay, and then I was asked, so let me just do this quick because I know some of you are sort of chomping at the bit for some assignment stuff. So how did we get this? Okay, so here, let me just repeat this. So we had, what did we have? We had 1 was equal to 2x lambda. We had 1 was equal to y lambda. And we had 2 was equal to, what was it? 2 is z lambda. So there's a question asking me how did we get, y was 2x and z was 4x and those sorts of things. So what I'm going to do is I'm going to solve this equation for 1 over lambda. So I'm going to write this as 2x equals 1 over lambda. I'm going to write this as y is equal to 1 over lambda. And then if I do this, I'm going to get z divided by 2 is equal to 1 over lambda. Okay. And so for example, look, both of these things are equal to 1 over lambda, right? So that must mean that they must be equal to each other, right? Or I could do something like these two equations are equal to one another. So that means that 2x is equal to z divided by 2. And that's the same thing as z is equal to 4x. Right? Christian, does that help? Does that make sense? Okay, cool. How to do a number of solutions via probability. No, it's okay. Doing old stuff does make sense. So, okay, so there's a lot of people who want me to kind of talk about basically all of the assignment. Give me just 1 minute, go refill my water and stuff, and I'll be right back. Okay, so just 1 minute. Okay, so let's see. So lots of people have been asking about the assignment, and I feel like I've gotten pretty much every question about the assignment. Yeah, okay. Now it's going to be a little bit tricky because I'm not, it's a very specific. Oh, I see. Okay. Why are you being weird, Zoom? What are you doing? Oh, that's why, because you're shit. Okay, hold on. Zoom being weird. right, fine. We'll share the screen. All right, hopefully it's not going to do that this time. Okay, good. All right. Somebody's asking about every question about the assignment. So, okay, so people who are asking about like parts 1 and part 2, can you be more specific? Like what part of question 1, part 1 and part 2 are bugging you? Right? Because we need to be specific, because again, I can't solve the problem for you, but I might be able to find something that's similar if you can tell me like what actually the issue is, right? So try and see if you can figure out a way of describing the issue that you're having. And I'll see if I can come up with something similar. Okay, what it's even asking. Okay, so look at the very beginning of part 2, right? It tells you, I mean, I can just write this part down because it's public info. So we're told UTX is f of x plus ct minus g of x minus ct, right? Okay, and then we're told as well u of 0x is what is g of x. Do you agree? Everyone asking about part 2, that makes sense, right? That's just, these are things that are given, right? In part 1, you're told u of 0 comma x is equal to g of x, and that ut comma x is this thing with capital F and capital G. Oh, you're right, it is plus. Okay, so far so good, makes sense? So how do I relate these two things? How do I turn the top equation into the bottom equation? Okay, hold on. So Arslan, exactly. So I'm not, because there's no derivatives going on, right? Don't make the mistake. Like these G's are unrelated, right? Like normally we would use capital G to be like an antiderivative, but these are just unrelated functions. But Arslan, absolutely 100% do what you said and set that, like, you know, do that to the top equation, and what you get is the bottom equation, right? Yeah, exactly. Okay, and then, yeah, exactly. Yeah, Edward, 100%. Agam, you're right. That's the answer that you get out, which is exactly right. And do you see that that's part 2? And then you do the same thing for the second equation. Yeah, exactly, Sam. Yeah, exactly. So part 2 should actually be really quick, right? You basically are just like plugging a couple things in and you're done. Yeah, oh, and exactly. Davin, you mean why does this equation even true? Like why do we give that? Yeah, exactly. It's given in the assignment. Well, I thought maybe you were asking like why in real life you would do that, right? And like in real life, you can imagine, you know, if you've got like a pool, you know, a bucket of water, then at time 0, right? Like I'm going to dump that bucket of water and I want to be able to model how that water, you know, falls or something. So at time 0, I have to describe what the water looks like. And then as I dump it, you know, that tells you over time, you know, you would solve this partial differential equation and that would tell you what is happening over time. Right. Okay. Sure. Arslan. Yeah. Yeah. And everyone keep in mind, like this is designed so that you don't need to do any one part to do the next part, right? Like if you want to answer question 4 and you haven't done 1, 2, or 3, that's fine. You have to use, you know, part 3 to answer part 4, but we give you what the answer is. Do you know what I mean? Okay, now about question 1, is everyone okay with that? I did talk about it a little bit in Tuesday's office hours, so you can check that out as well. But for question 1, part 1, is everyone okay with that, or do I need to talk about that a bit too? where do we use u? I mean, u is the answer, right? U is the solution. So Brandon, the linear system is part 2 and part 3. Right? Simon, what part is partial derivatives? Right, yeah, exactly. And a bit of chain rule as well. Yeah. Edward, how can the constant still be the answer if we said? Because you differentiate, right? So Edward, when you differentiate, like it's like, here, let's say I gave you this. So f of x is just a function of one variable. And then I said, here, define a new function, which is f of cx squared or something, right? And now if you differentiate f of cx squared, what do you get? You get 2cx f prime cx squared, right? Because that's how the chain rule works. And notice that the constant there came out, right? Are you supposed to use only week 10 content? Yes. Yeah, Natalia. Yeah, you shouldn't need any more than just partial derivatives in order to do it. So it's h of x equals g of x equals. Let me. So one of the equations, Brandon, is literally the first equation in part 3. Like that is exactly one of the equations. Okay, and then you like look at what you're trying to solve for, right? The question is saying solve for capital F and capital G. Do you see another equation on that sheet of paper that involves capital F and capital G? And not their derivatives, just literally capital F and capital G. Right. Okay, so try that and see what you get. I don't know what you mean by subbing, because it is a system of equations. Like you're going to have to do some add this equation to this equation or row reduce a matrix, but it's a 2x2 system, so it shouldn't take that long. But just try it. See what happens. And don't worry about the like of x's, right? Like just and the integral, just call it like I or something if you don't want to carry it around with you. But yeah, see if you can't sort out what it should be. And I mean, like, again, we've given you the answer and you can see that a little g appears and the integral sign appears. So that's kind of like a hint as to which equations are coming in. How do we integrate question 1.3? You don't. Right? So in question 1.3, and this is a couple of people have asked this question, you don't have to compute that integral, right? Like you literally just leave that integral the way it is. So you're not trying to compute it because you have no idea what the function h is, right? So you're just leaving it the way it is. Yeah, I mean, simplify as much as you can for sure. Yeah. Are we looking for a system of equations in question 2? So not yet, Owen. Like you're not looking, like it's in question 3 that you're looking for a system of equations, but the system of equations, part of it comes from part 2 and part of it comes from part 3, right? So again, you're trying to solve for F and G. So if you're trying to solve for these two things, you probably want equations where those things show up, right? And there's only 2 equations. And I told you, right, you can solve every single part of this problem without doing any of the previous parts. The 2 equations that you need, right? So we're trying to solve for 2 things here, capital F and capital G. So we need 2 equations. There's literally only 2 equations on the paper before this that have both capital F and capital G in them, right? So those are the only 2 equations that you could use. In part 1, do we need to use equation 1? Oh yeah, for sure. Well, I mean, it's not that you need to use equation 1. You're trying to show that equation 1 is true, right? So you're trying to show that if u of tx is of the form that's given, that di squared u di t squared is equal to this, right? So Shani, what you could do is you could differentiate, or you could compute this, and then you could compute this and see if they're, equal to each other up to c squared. That's what question 1 wants you to do, or part 1 wants you to do, right? It wants you to check that this equation is satisfied if u of t of x has this form. Oh, question 2, sorry. Question 2, part 1. Wait, does it even have parts? Oh, I see. Yes. Yes, Owen, yeah, you do need a system of equations. But it's the gradient, right? So you're going to set the gradient equal to 0, 0, 0. That's going to be 3 equations, and there's going to be 3 unknowns there. Do you know what I mean? So compute that gradient, set each of its components equal to 0, 3 equations, 3 unknowns. Okay, where are we? I've kind of been jumping all over the place. Who's still outstanding? Who needs a question answered? Arslan, where are you subbing in A? That's true, but why would you sub in A? I mean, I'm kind of jumping, Ali, back and forth depending on who's asking. So Arslan, are you bugged by the show that for any constant A, this happens? Oh yeah, okay, yeah. So no, it's just saying that's the bottom bound of integration. Like you don't care what it is. So we're just saying show that this is true, right? That the integral from A to X of H is something. But if I change that number, right? So if this number is 1, then if I change the number to 2, I get something on the right-hand side, but instead of using, do you know what I mean? Like here, the A's on the right-hand side would be 1. Here, the A's on the right-hand side would be 2. Do you see what I'm saying? Like if I wanted to show that this was true, let's say, it was this or something, then that would be the same thing as showing, oh, the integral from 2 to h is f of 4, or the integral of 7 to x is f of 49. You know what I mean? We're showing that for every a, this is true. Christian for 1.3, just HFS at 1.3. I mean, you just don't have an equation to sub in there, Christian. Okay, so Arslan, what it's saying is just, we don't care what the lower bound of integration is. Just show that if you choose a lower bound of integration and you happen to call it A, then you get the thing on the right-hand side, which also has A's in it. Right? So just fix an A, whichever, it's just you just called it A. In fact, if you want, do it for a specific A first. Okay. If it's bugging you right now and your brain's kind of like rocked, just set A to be 0 and solve it. Okay. And then show that if A is 1, you get something else. Yeah. So Christian, does that answer make sense for you? Like, it's the sort of thing like, we've got an equation 3x plus 4y is equal to 7, 2x plus 8y is equal to 4. And a lot of you are asking me like, oh, well, how do I solve this system? And I'm like, well, you know how to solve this system. It's just things look a little weird right now because instead of them, some of these things are functions, but it's a linear system. It doesn't matter whether I call it 3f of x plus 4g of x is equal to 7, 2f of x plus 8 g of x is equal to 4, right? Like if you can solve this system of equations, then you can solve this system of equations, right? They're the same thing. It's just I happen to call my variables something else. I called them weird names. I called them f of x and g of x. Does everyone see what I'm saying here about that linear system of equations? I think people are getting hung up on the fact that our variables here are functions, but it doesn't matter. The way that you solve them is the same way that you would solve any linear system. Right? Like I might do, if this were literally my system of equations, I'd probably do something like -2 times the first equation plus, the second equation, or put it into a matrix and row reduce the matrix. And the answer you get isn't x and y. The answer you get would be f of x and g of x, right? Is everyone okay? Does that make sense? Or instead of a 7 over here, you've got like an h of x or something. Instead of a 4, you've got a g of x. Like I think you guys are maybe getting hung up on the fact that these are functions instead of like numbers, but it's still a linear system. Everyone okay? The silence is freaking me out here because like, I feel like some people maybe aren't okay, but yeah, Brandon, it's the thing that you did at the beginning of 3. That's the other equation. Like, look at what the answer is. The answer has the integral of h in it, right? So the other equation you use also has to have the integral of h in it. Otherwise, there's no way that it'll show up. Right? Like, okay, maybe I should actually just do this weird example here, because I think it's bugging some of you. Like, let's say this, this isn't a linear system, but if I asked you to solve this linear system, could you? And yeah, I might do something like -1 times equation 1 plus equation 2, and that, what would I get from that? So I would get negative f of x is equal to h of x, or sorry, negative h of x plus g of x, right? Boom. So that tells me capital F of x is h of x minus g of x. I've now solved for that function, right? Just like if I gave you the equation 2x plus 4, maybe let me call these something else, 2y plus 4z is 7, and 2y plus 8z is 4, or sorry, 3. If you did exactly the same thing, that would let you solve for y, right? Brandon, if you don't want to carry that thing around, just call it I, right? Like, it doesn't matter. Just be like, let I be the integral from a to x h of t dt, or whatever variable we used, right? And then just write it as I everywhere. And then when you're done and you found it and your answer depends on I, just replace the I with the integral, right? Yeah, I wouldn't even call it, yeah, for sure, I of x. Yeah, actually, I missed your previous message, but yeah, exactly. Call it I of x. So C is also a constant, and we make a linear system using the C's. No, C is just hanging, it's just coming along for a ride. It depends on what you mean by a linear system using the C's. Davin, like, there will be C's, the C's will show up, but the C is a fixed constant at the very beginning, right? Notice that C shows up in equation 1, right? That C shows up there. So that's fixed from the very beginning. And it will, appear in your linear system of equations, but, it's depending on what you're sort of getting at and implying. I'm not certain, like you might be meaning something deeper there, but it's coming along for the ride, but it's not a critical part. It's just, it's got to show up. Okay, now for those of you asking about question 2, are we good? Is anyone still stuck on question 2? And we did do a poll question that was like question 2. Let me see if I can find it. Which poll question was it? So question 5 of week 10 is very similar. And then we might have done one this week even, actually. Let's go 1.3. So are we supposed to integrate h? No, don't integrate h. Just leave it as the integral of h. Okay, do not integrate that integral of h thing. I think is throwing off a bunch of you too. Just leave it as the integral of h and carry it around with you, right? You're not supposed to integrate that in any way, shape, or form. Yeah, I don't want to say you're ignoring the C's, Davin, but like, yeah, they're just coming along for the ride. They're not a critical part of what you're trying to do, right? But yes, your linear system is made up of different functions. The C's are coming for along for a ride, but you're not ignoring them, right? Again, it's sort of like the idea is that you should get something that looks kind of like that. Not exactly, right? Like, what if there are a bunch of C's in here? You know what I mean? Like, they're there, they're part of the equation, but it's not that big a deal. Okay. Anyone on question 2? Brandon, I'm glad to hear it's coming together. But yeah, was there anything on it? Because I've spent a lot of time on question 1 here. I just want to make sure I haven't like abandoned any of the question 2 people. And where is, I thought we did one like this. Yes. So question 6. Oh, maybe we skipped question 6 though. Okay. I don't know. There's still a lot of silence. Kind of freaked out. Right. Yeah, exactly. That 1/2 and the 1/c come from that. Right. Yeah. Exponential can never be 0. Absolutely. Right. No. Yeah. It's not coming from the antiderivative. It's coming from the linear system. Yeah. For solving the system of equations, in fact, Owen, yeah, no, it's very similar to what we did today, and right, because it's a nonlinear system of equations. So the advice I would give is to do something very similar to what we did today. And, you know, to try and look for an opportunity to start doing cases and break your casework up. Right. So like go back, take a look at, you know, what we did today and how we solved that nonlinear system of equations and start to do some stuff like that. It's actually very, very similar, very similar. Okay, anyone else? Has everyone sated? Everyone's more or less happy? Yeah, no problem. Yeah, well, I'm glad, you know, an extra couple 1% or whatever here and there, no big deal. Yeah, I mean, like, you know, it's the sort of thing that makes, I know, a big difference for a lot of you. And in fact, if you've just been participating all year, right, there were those 2 quizzes earlier and this 1% quiz here, there's just free 3% that you could do just by doing a couple of pretty easy things. And that's a GPA percentage, right? Like that actually makes a difference. Right, exactly. Whether you give consent or not, it makes no difference. You get the 1% just for filling it out. Because the thing that's more annoying for me is if you don't fill it out, that's an automatic not consent. But like, it's basically to force you to actually do it so that, because otherwise, if you don't fill it out, you didn't consent, right? But if you want the 1%, you actually have to go and make a decision about which one you want to do. So now, obviously, I would prefer if you consented, just because like legitimately, it makes no difference to you, right? But it will make a difference to the data, like when we actually run the data to see what difference it made. But you don't have to if you don't feel comfortable with it. For what? Okay, Christian, I see it. Give me a second. Yeah, Brandon, that's it. That's all you have to do. Yeah, for question 2, when you set the gradient equal to 0, each partial. Yeah, exactly, Arsalan. Yeah, and that'll give you 3 equations and 3 unknowns, right? And they're nonlinear, but that's okay. And then you solve it. 11-28. Oh man. It's too late now. It's too late now, Dad. I like it, but it's too late now. Passing grade is 50%, but the grade to continue in commerce is 63. Right. No. Pass is 50. Yeah. So if you get 50 above, it's a pass, because a fail is brutal to your GPA, right? But yeah, I mean, most post requirements have it as a 63. So yeah, in some sense, your pass is really a 63, but it won't, nuke your GPA if you get like, 55, for example. You might not qualify for post, but again, your GPA will survive. Okay, so 11-28. Sure, so this is, where's the function? F of x, y equals e to the xy. And you've got 2x squared plus 3y squared is less than or equal to 6. So this has 2 parts to it, right? And in particular, you actually have to do the interior as well. So you have to find the critical points and then do the boundary separately. So you kind of need to do the interior first. So that's going to be 2x squared plus 3y squared is less than 6. And then you have to do the boundary. So either way, we have to compute the gradient. So why don't we do that first? So if we compute the gradient, we get y e to the xy, and then we get x e to the xy. That's equal to 0, 0, precisely when xy is equal to 0, 0, right? And then you have to do your Hessian test, right? And compute what that's going to be. So if we compute the Hessian, what are we going to get? So derivative of that with respect to x, that's y squared e to the xy. This is going to be x squared e to the x. Well, I might need more space. E to the xy times y plus x, I think. Right, so if I differentiate y, derivative first times second, with respect to x, yeah, that looks right. This is going to be the same thing by Clairaut's theorem, and this is going to be x squared e to the xy. So if I plug in 0, 0, what do I get? So I get 0, 0, 0, 0. So this is degenerate. So the second derivative test actually can't tell you, whether this is a max or min. So we're going to have to come back and figure it out after. This is 11-28. So it's not like directly related to a question, but it is a Lagrange multipliers question. So Natalia, that's from like the book, right? The notes. So that's the interior. For the boundary, the boundary is sort of more important here anyway. So let's parameterize our boundary, which is what? So we're going to use 2x squared plus 3y squared minus 6. That way the gradient of g, 4x, 6y. And then if we use Lagrange multipliers, so we have the gradient of f is lambda times the gradient of g. So that's going to give me y e to the xy is 4x lambda, x e to the xy is 6y lambda. Okay. All right. What do I do? So the way I would probably do this. So again, and let me include again our boundary thing, 2x squared plus 3y squared equals 6. Okay, so here's what we have to do. Now, the way I would do this is as follows. I look at this and I look at this and I say, man, those are close, right? Those are really close. So what I want to do is I'm going to multiply the top equation by x, and I'm going to multiply the second equation by y. And I'll show you why. So multiply by x, multiply by y. Okay, so if we do that, what do we get? So the first equation becomes xy, becomes xy e to the xy is 4x squared lambda. Second equation becomes xy e to the xy is 6y squared lambda, right? Does that make sense? So I multiplied the first equation by x, and I got the this thing. And then if I multiply the second equation by y, I get that thing. And the reason why I did this is because notice that the left-hand sides of both of these equations are equal. So that tells me 4x squared lambda is 6y squared lambda. Does that make sense? Right. Yeah, exactly. Gets rid of the exponential, which is really, really great, but also is going to now set me up for cases, right? So basically what I want to do here is I want to divide by that lambda, right? I want to get rid of that lambda. But before I can do that, I need to know lambda is not 0. So that's case number 1, right? So this is a really important equation. Let's call it star. So I want to divide by lambda. Again, need to make sure lambda is not 0. So let's set lambda to be 0 as our first case. Okay, well, if lambda is 0, then I go back up here and I look at, these two equations at the top here. And what does that give me? That gives me y e to the xy equals 0 and x e to the xy equals 0. And that's only possible if x and y are both 0. Right? Because e to the x y is never 0, right? So if I get y times something which is never 0 is equal to 0, then y had to be 0. Does that make sense? That's okay? Okay, but this can't be a solution because the third equation says that 6 has to be 2x squared plus 3y squared. That would be 0 plus 0, and that's not possible, right? So this is not a solution. And we can throw this case away. So great, lambda is not 0. Okay, so lambda is not 0. We go back to star. So from star, right, we can now cancel out the lambdas. And while I'm here, maybe I'll cancel out the, there's a factor of 2 on each side as well. So I'll get 2x squared is 3y squared. So far, so good? That makes sense? Okay, and now what I'm going to do is I'm going to take this. Remember, we still have this equation here. So subbing into this equation, 6 is 2x squared plus 3y squared. So, okay, great. 3y squared is, according to this equation, 2x squared. So I get 2x squared plus 2x squared is 4x squared. So x squared is 3 halves. So x is plus or minus root 3 over 2, right? And then I know that 3y squared is 2x squared. So that means that y squared is 2/3 x squared. So that's going to be 1. So that implies y is equal to plus or minus 1. All right, so that gives me my 4 solutions, plus or minus root 3 over 2, plus or minus 1. And now plug them in to see which is your max and which is your min. Which of these 4 is your max and min? But again, remember the original function, we don't actually have to plug them in, right? The exponential is big when its exponent is big, and it's small when its exponent is small. So the max is when both of the signs are positive, and the min is when when one sign is positive. Okay, no, sorry. The max occurs when both of the signs are the same because you're multiplying x times y. So if both x and y are positive, that number in the exponent is positive. If both numbers are negative, both numbers, x times y is positive. And it's a minimum when the signs are different. So that's how we answer that question. Okay, good. It's a little bit involved, but it's the same sort of thing. And what you'll probably notice is that the way I solved that question was different than the way I solved the previous Lagrange multipliers question, which was different than the way I solved the previous Lagrange multipliers question, right? So all three of the Lagrange multiplier questions that we've done today all had sort of different approaches and techniques. Now, you start to get a habit of, or get the hang of the sorts of things that you might do when you want to solve these systems. This trick that I did here where I say, oh, look, these left-hand sides are really, really close. So let's just multiply by a couple of things to make them equal. That's a really common trick there. And I, again, sort of strongly recommend that you internalize that one. But yeah, I mean, this is, again, what I'm saying, right? Like solving these equations is very ad hoc. You need to really play with them and do enough practice in order to be able to see how you solve them, because there's no algorithm. And the way that you solve them is really going to depend on what these equations are. Okay. So that finishes us off today. Everyone good? Everyone more or less happy? Let me take a look. Yes. Yeah. 1126 is also a Lagrange multipliers question. Yeah. No problem, Arslan. See you later. Next week is just office hours. So technically, everyone, this could be the last time I see a bunch of you. So that being said, this is the last time that you come to lecture. Thank you. It's been a good class. I did enjoy it. I mean, we were online, which kind of sucked, but other than that, I had a good time. You guys made it really easy to come to class. Yeah, other than that, yes, absolutely. Dad, just working for that extra 1%, right? No matter what. So yeah, everyone, if I don't see you, good luck on your exams, including ours. Have a good break. Hopefully you see me on campus next year. If you do, give me a shout, say something. Again, don't be upset if I don't recognize you, because none of you had your cameras on all year. So I have no idea what any of you look like. I know your names, but I don't know your faces. So, come over, meet me, introduce. Thanks, Dad. Yeah, that's nice, right? Not everyone says that about their math class, but but yeah, if you see me, come over, introduce yourself, let me know who you are. Thanks. Yeah, exactly. I'll be around Deerfield. That's where my office is. But then otherwise I go wherever I got to teach. Okay, everyone. So seriously, it was a good year, all things considered. Best of luck. I hope you crush everything, including our exam. Go ahead and crush it. Couldn't be happier if you did. And hopefully I'll see you in September. Okay. Bye, everyone. Yeah, I'll be there. Brandon. Okay. See you, everyone.